जब स्टार्ट हो बता देना मेरे को ना। Hello and welcome to the fourth lecture of Advanced Materials Chemistry Device Materials part. In the last lectures we saw photovoltaics and we will continue for third generation solar cells. Like in last lectures we saw that almost all the practical devices are made using semiconductor materials because it is easy to control the movement of electrons and easy to control the number of electrons also in that. Then elemental semiconductors are silicon, germanium, and compound semiconductors, 3/5 and 4/6 elements are most commonly used in these practical devices. We also saw that there are four kind of basic device building blocks, which are metal semiconductor junctions, PN junctions, two different kind of semiconductors having different band gaps, S1 and S2, also called as heterojunctions, and metal oxide semiconductor structures. Any one or any combination of these four building blocks can give you a working device. Then we saw solar cells are typically PN junction based devices and they convert light into electrical energy. The important parameters for any solar cells are open circuit voltage. What is that open circuit voltage? When you are not drawing any current, then whatever is the maximum voltage is generated by the solar cell, that is called open circuit voltage. And short circuit current is the maximum current which can be drawn from the device. This is when we do short circuiting. Yet in this situation, the voltage will be 0. And then there is a fill factor which gives where the maximum efficiency is obtained for the value of voltage and current. Then for the solar cells, absorption of incident radiation is very crucial, and therefore material selection becomes very critical for the photovoltaic devices. In these devices, electron and hole pairs created should be efficiently collected at the electrodes before they recombine. So basically what it says that in the solar cell, the carrier lifetime should be relatively high. Before they recombine, they should get collected. For maximum absorption of solar spectrum, multi-junction solar cells can also be used, where you are stacking one solar cell over other solar cell, and the selectively some part of spectrums are absorbed in all three or four or what, how many multi-junctions you have. Then we also learned that photovoltaic technologies can be categorized into three generations, first, second, and third generation. And in the first generation solar cell technologies, single crystal or polycrystalline materials were used in the form of thick wafers. Silicon and gallium arsenide were most commonly used in this generation. Thin film based technologies were utilized in the second generation solar cells, and the important devices also we saw yesterday. The material requirement was reduced due to the thin film and the thickness of this was very small. However, at the same time, efficiencies were also less for these devices as compared to the first generation devices. Some of the examples we saw amorphous silicon, cadmium telluride, copper indium, gallium diselenide CIGS solar cells. And the thin film devices are generally having P-I-N structure, means one side is P-type of semiconductor, very thin layer, other side N-type of semiconductor, very thin layer, and in between you have a intrinsic semiconductor. So this is we saw that is the first generation, second generation we have covered. Now we will come to the third generation in today's lecture. So these are organic solar cells, dye-sensitized solar cells, perovskite solar cells, quantum dot solar cells. We will quickly see how these solar cell works and what is actually difference between these solar cells and the other solar cells. So if we see first inorganic photovoltaics, we used silicon or inorganic semiconductors. So in these third generation solar cells, organic semiconductor materials are used for making these devices. So the organic semiconductor materials, the semiconductor are two types. One is conjugative polymers and another are small molecular. Small molecules are these are two organic semiconductor type, two different. So appropriate doping in these materials causes delocalization of pi electrons, and that is the cause of the semiconducting properties in these materials. These are some examples of organic semiconducting materials. There are actually plenty, but some of the components which are very commonly used and most widely used are in case of small molecules, pentacene, ruberine, and PCBM. PC6071 also, and that is there are so many in this category. And similarly in polymers also we have this is also very commonly used poly-3-acyl thiophene, also called as P3HT. Then polyphenylene vanillin, that PPV, and polyfluorine, and there are many. So these are just some typical examples of the organic semiconducting materials. First is, why do we require to go to organic when when inorganic solar cells are doing fine? Then why do we go to organic? So why there are some issues with the inorganic devices. First of all, they are very expensive. Then high purity materials are needed. Fabrication process is quite complex. You need crystals. In fact, single crystals, or even in thin film also you need complex deposition techniques, processes also involved, and these are not flexible. Generally, these inorganic solar cells are rigid. Some solar cells use toxic materials as cadmium and arsenic, etc. And gases also silanes while we make the devices. Therefore, organic solar cells are a possible alternative. What are the advantages of organic? First thing, they are low cost. Right now, the cost may be higher because there are new materials and making of new materials are expensive. But once a material is finalized, in that case, mass production will reduce the cost considerably. Then they are good absorbers of light, though not exactly better than inorganic, but they absorb reasonably well light. Processing is very easy. You can do solution processing, prepare in the laboratory also. Then flexibility, the device are flexible, can be made flexible, can cover a large surface area and with cost effective way. The properties of materials are tunable because now you have several molecules, and then you can slightly alter the molecule with some ligands, and then the properties can be changed. And they are eco-friendly also, because if you can choose biodegradable molecule, then the devices are eco-friendly. There are some challenges also with organic. First is, it is evolving technology. There is not the devices, not much devices are commercialized, very few. They are also not very stable. So the technology is still evolving. People are still working in laboratories or at industries for doing research. The efficiencies are lower as compared to inorganic, in fact, quite low. And there are the main issues are degradation and stabilities. They are not very stable. They degrade with time. And in the organic, there is a problem of batch to batch variation. You make a device with one batch of the organic semiconductor and make device from the another batch of the organic semiconductor. Then you will have a variation. So optimization is slightly tricky and difficult. Material purification is also difficult because these are polymers, and it is very difficult to purify. So with this, first let us try to understand what is the main difference between inorganic and organic semiconductors, because in both the devices we are using semiconductors. So as we saw in the first lecture, also a little bit in the second lecture also, that inorganic semiconductors are basically the crystals which is having all a periodic structure in all three directions. So because of the periodicity is throughout the crystal, and if it is a perfect crystal, throughout the entire crystal. So then because of that periodicity, you get bands, and that bands are throughout the crystal. So in inorganic semiconductors, you have valence band and conduction band, and these are throughout the crystal. So if an electron and hole pair is generated by, suppose light falls, and it is absorbed by an electron here, so a hole will be created here and electron will go there. So once it reach there, then the electron is ballistic, means it can move throughout the crystal. There is no restriction on that. So because bands are over the entire crystals, it is not like that they are not to a certain place. However, if you consider organic semiconductors, there is no long range order. So if there is no long range order, periodicity is also limited to certain small chunks. So during that chunk only, there will be the rules of these bands and all these will apply for that period. So you will get, in that case, it will not be actually bands, but it will be a homo-lumo kind of structure. So the band is, then this is not, the thickness is very less, because this thickness depends how many you can say molecules are there in that cluster. That we have understood from the first lecture. So now you have one level this, and another level is this. So this level, the lowest one is called as highest occupied molecular orbital, and the upper one is called as the lowest unoccupied molecular orbital. So now you imagine a situation where the continuity is not throughout the material, but through continuity is there through small crystals which are actually kept together with each other, but they are not having a same periodicity over the entire crystal. So now you have one material here, one chunk here, and another chunk will be at little bit distance somewhere here. So you will have another homo-lumo. They are slightly different, but at slight distance, but there will be gap between these two. So it is not now a situation like in inorganic semiconductors. You have a situation where now when a light is absorbed, the electron will move from this place to this place. It will remain bound. So electron hole pair are not generated, but excitons are generated, which are coulombically bound. They will remain at this HOMO-LUMO only. Now, so there is a very good probability that they can recombine, because the first thing is that if you want to stop the recombination, they should move to the another one. Now, if there is another, you can say same level here. So this carrier, this electron which is here, there is no continuity between these two. So it has to hop from this to this, kind of either quantum tunneling or some other way. So it has to hop, so that automatically the mobility becomes very low. So that is the reason why the efficiency are low in these devices, because electrons are not that mobile as these were there in the inorganic semiconductors. So organic semiconductors are carbon-based materials processing semiconductor characteristic. So the materials which are possessing semiconductor characteristics. Atoms within an organic semiconductor molecule are bounded by conjugated pi bonds, while molecules are bonded to each other by weak van der Waals forces. So you have one chunk and then another chunk. They are bonded to each other by van der Waals forces. There is no actual bond. However, in case of inorganic semiconductor, you have a covalent structure which is there throughout the entire crystal. In organic semiconductors, HOMO and the LUMO are the analogous to valence and conduction band respectively. However, they are actually not same to the valence band and conduction band. This you must keep in the mind. HOMO and LUMO are different. These are basically for molecules only. However, valence band and conduction band are for the crystals. Valence band and conduction band, you can see the width is very, you can say, more as compared to HOMO and LUMO, where the width of these levels are small as compared to the valence band and conduction band. There are some other problems. There are low carrier mobilities for organic because crystallinity is not there. So as I already said that once electron moves into conduction band in inorganic, then it is ballistic throughout the crystal. But it has to, in case of organic semiconductors, between two small, you can say chunks, it has to hop through. It is not, the material is not single crystalline. So hole mobility, if you say, it is typically 0.01 or nearly 20 for small molecules. However, if you see in silicon, it is very high, 500 centimeters square per volt second. And if you see the electron mobility, it is about 0.1 as compared to very high, about 1500 centimeters square per volt second for silicon. So the mobility is low. So the carriers which you have generated, they move relatively with a very low speed. Then carrier diffusion length is also, obviously it has to be low as compared to in silicon. Silicon, it is approximately 300 micron. However, for our organic semiconductors, this is in the nanometer range. Carrier lifetime for silicon, it is about 1 millisecond. However, in organic, it is in the range of nanosecond to microsecond. If it is in a singlet stage, it is very, very small, and then if it is in triplet state, then obviously it can stay for a little longer. And why it can stay longer? Because the transition from higher level to lower level is forbidden. Then stability, inorganic materials are highly stable compared to organic materials that are generally reactive with atmosphere and so photon induced degradation. When I'm saying inorganic, the organic materials are not very stable, I'm not talking in general, but I'm telling that those organic materials which are being used in as a semiconductor for the photovoltaic purpose, though are several organic molecules which are very stable also, but these are specific case. So there are a lot of research are going on where we can find out stable organic materials which can be used in the photovoltaics, still in the research scale. Now preparation for organic flexible and low cost substrates are there, and room temperature solution processes can be used for fabricating organic devices. However, for like silicon based devices, you need high temperature, energy intensive and expensive materials and processes to make the devices. Therefore, we can conclude that organic materials or organic devices have advantage of low cost and easy processing, but need further development because they have not been yet developed completely or to a level where these can be commercialized and put in the market. With this, let us we can recall our earlier class how a solar cell was working. So on the basis of similar understanding, we can make a device on using semiconductors. In organic semiconductors, in place of PN junction, we prefer to call them as a donor and acceptor. So like in silicon, you have N-type layer, you have P-type layer, both are joined, and then contacts are made and these two ends, and then these are connected through a circuit to the load. Similarly, for the organic solar cells also, we can think in the same situation. You have a cathode and you have a anode, which is transparent conducting oxide. It can be ITO, which is most commonly FTO also. Two most commonly used transparent conducting oxide. What are these? These are the materials which are actually transparent but conduct also. Generally, all the metals, because these metals are having zero band gap, we saw in the first lecture itself, because these are zero band gap materials, so whatever light will fall them, they are expected to absorb it completely. So that is the reason why metals are not transparent. You see any metal, you will find that it is not transparent because it has a zero band gap. Therefore, whatever light falls on that, the electrons absorb it and go to higher levels. So they do not transmit. However, certain materials which are like they are transparent. So you need to find a transparent material which is conductive also. So ITO and FTO are two materials. They work on a different principle on the basis of vacancies. How do they conduct? But it is not the same conduction mechanism as it was in the metals. So you have this, and what is the advantage of this? Because then you can illuminate this solar cell, so light falls from this side and it goes through this transparent conducting oxide, and through this it reaches the junction. So this is a typical solar cell, which is we call as a bilayer solar cell. It is having a acceptor layer, it is having a donor layer, it has two electrodes, and then connections. Light falls, and then similar way the current flows. However, there are a lot of problems in this. It is not, as I said, what that in the slide of difference between inorganic and organic semiconductor. So it has a very poor mobility, even if electron hole pairs are generated at these 2 points. It is very difficult. First thing is they are excitons now. It is not single crystal. The entire this block is not a single crystal. So they are localized levels. So if this electron and hole pair, or we can say exciton, is generated, first it has to be converted into electron and hole pairs. Then if this electron has to move from this place to this place, same way hole has to move from this place to this place. So how it will move? The mobility is very, very low. Therefore, it is very difficult for these devices to have higher efficiency. We will see a typical operation of polymer solar cells. You have a donor, you have an acceptor. These are the typical energy levels in the form of HOMO and LUMO, not in the valence band and conduction band. And you have cathode work function will be like from this, so from vacuum to this. Similarly, you have a anode. You have to find the materials, anode material and cathode material. The level of this should be matching to these levels, so that electrons can flow. Now, this is in the case of individual donor, acceptor, and cathode energy levels. When you combine together, then we understand that it becomes a one system. And if it is a one system, then the Fermi level should be constant throughout the system. And when I am drawing this diagram, it is not a general diagram. I am assuming one donor molecule, one acceptor molecule, and then cathode and anode can be more, no problem. So please keep it in mind. This is not that you have entire material and we can draw this kind of structure in that. And there's one more thing you keep in the mind when the photon falls and there are a lot of, you can say, electron and hole generated. In that case also this Fermi level will change. So this diagram is just to explain you the process so that and you can get an idea. So now a photon falls and electron and hole pair are generated, but these are bound. These are not electron hole pair. Actually, it is an exciton. So now this exciton is, so it is a, you can say both are, consider them together, though energy is higher. Now this is electrically neutral. So even if you can see there is a gradient of potential, we consider the built-in potential due to the difference of work function of this and this material. But since it is electrically neutral, it is not going to face any force, even if there is a voltage, because for a pair or it to move under a or to experience a force, it need to be charged inside an electrical field. So since it is not charged, so it will not feel any you can say any force which can compel it to move to this side, electron to this side or hole to this side. So it can move in any direction. First thing is that it's a very highly probable that these electron hole pair will combine and emit the same photon. Next thing is that if it will move by hopping. So if it is only one molecule, let us not consider the hopping. So it can move in any direction. So in any direction, 4 pi direction. So the probability of moving this to this side is also very low. Suppose we consider it has moved to this direction. Now, to separate this electron hole pairs from this exciton, you need a certain energy, activation energy. So this energy is provided by the difference of these two levels. So now, once they reach at the boundary, so it is absolutely necessary for this exciton to reach at the boundary where it can dissociate in the electron and hole pair. Now it has dissociated because of this energy difference. So you can just think how the probability is still reduced. First thing is that exciton is it is very highly probable that it will recombine. The lifetime is very low. You can see as compared to the inorganic materials. So and then there is a less probability that it will reach to the boundary where electron and hole pair can generate. So suppose it has reached, then there is also possibility that it can back recombine, because movement through this also the mobility is also low. Let us assume everything is favorable and it has moved. So when it moves, it reaches the junction, then it is collected by the cathode, and then the hole is collected by the anode, and then the current flows through the circuit. It is just for like understanding how a solar cell works. So now we understood that the exciton has to move to the boundary. Before it moves to the boundary, it should not recombine. So now this typical distance, this is called as the diffusion length, which is very low. It is of the order of few nanometers. So let us consider about 20 nanometers. So if an exciton is, if photon is absorbed in this region, a photon is absorbed in this region and this exciton has been created, it cannot reach up to this junction because the diffusion length is this much only. So the excitons which are created only in this area, they are only probably will give you electron and hole pair. I am again saying probably. That is not necessary. If an exciton is created in this area, that will definitely give you an electron hole pair. So let us consider. So this thickness is very low. So suppose you are depositing a p type of about 100 nanometer, which you can control in normal solution processing method. Then you have 200 nanometers of it. Out of that, only 20 nanometer is useful. That is also not 100% useful. So that is the reason why a bilayer kind of solar cell have not worked at all. So efficiency are very poor. It is less than 1% in normal cases. In a perfect device, if you make everything perfect, you can get about 1% of the efficiency. So because of low exciton diffusion length. So if we cannot increase the exciton's diffusion length, because this is material dependent, so we can try we can try to bring these junction together. So what is the way by doing by which we can do this kind of thing? That kind of you can say methodology is called as making a bulk heterojunction. Bulk heterojunction means you have this material, in place of depositing one material or another material, actually you blend them. If you blend them, you will see that you just imagine you are just blending two different materials. So you will, if you blend them perfectly, so you can have this kind of structure where one material is this, another material is this. So now effectively you are increasing the boundary, and the dissociation, the exciton dissociation takes place at the boundaries only. So effectively, though the thickness is 100 nanometer only, but you have increased the you can say the area where the boundaries exist. So if suppose anywhere in this material an exciton is formed, it can try to reach to the boundary and get dissociated and in the electron hole pairs. But there is another problem now. See, this is the situation we have drawn as per our convenience in an ideal way. What is that? So, okay, so this all the like donor material will get connected to this, all the acceptor material will get connected to this, but that is not the case. Now, when you are blending, you don't know which one will get connected to which one. So that is also again a probability, but it gives you better. Now you see another problem. Now this entire material is actually connected between these two electrodes. So even if you have brought an electron to this level, to from the it was suppose generated somewhere here, you have actually the holes you have brought to this or electron to this can easily, because there is a continuity, it can move through this way to metal electrodes, it can short. So that is also another probability. So but it is giving you better result as compared to the bilayers method. Now this, because the mobility of this material is very low, therefore this chain, which is having quite longer length, about the length of you can say the or thickness of the device, so and the mobility which is low, it comes to help us here. So electron which is here, actually it will not move this way, rather than it will try to move in this way because it is having higher conductivity. So this is the same thing I have explained in these two different pictures also. Here it is generated, it is collected here, and then it moves to this electrode. Similarly, the holes moves through this electrode. Same way, suppose it is generated here, the exciton is generated here, it moves to the boundary, here it gets dissociated, and electron comes here, hole comes here, then electron moves through this way, it reaches this electrode, and hole moves through this way, it reaches this electrode. So the same thing I explained in another way. So now in place of like making entire blend, here this problem can be further reduced by making finger kind of you can say arrangement, this arrangement, where you have this is one electrode, this is another electrode, and then so you can have more area where the electrode is connected to your blend. So it is like this here. So now you are making this finger kind of thing. So this is one contact, this is one metal, this is another contact, another metal, and then you have make this finger kind of thing, or over that finger you have deposited this blend. This blend. Now whenever these electron hole pair are generated in this active layer, this blend is we call active layer. So in this active layer, this can they find very near a boundary here, and here they can get dissociated, and then the electrons are connected to this side, they are collected, holes are collected to this side. But these are still the probability, you cannot say 100% that all electron holes pair which are created, or all the excitons has been converted to electron hole pairs, and all the electron hole pairs have still been collected at the contact. So that is the reason the probability is low, and eventually the efficiency is bound to be low. So there are one more thing, there are contacts, these contacts are in, we need to have another material which are actually providing you a level which is very close to this level. And similarly, if you, and that kind of levels are called as hole transporting layer. Similarly, if you find a material which is having energy level which very close to this level and make here, that is a that is we call electron transport layer or electron conducting layer. So this electron, now this hole, though it is actually inside the same material, this side and this side is also connected to the same material, but it will prefer to go to this side because the energy level of this material, which is a hole selective layer, is very close to this layer. Similarly, the electron, which is having a energy level here, and a material which is having a energy level here, the electron will prefer to move this way rather than to move this way. So the material is connected to both the materials, but electrons will move in a direction where an electron selective contacts are there. So these materials are called electron transporting material. These are called as hole transporting material, and these materials plays very important role in the extraction of holes and extraction of electron from these solar cells. So this kind of this finger making kind of thing, and the bulk heterojunction has advantage of higher surface area, and it allows the use of locally thin absorbers, because you are putting absorber on a thin layer, as a thin layer, and then poor thickness control, pinholes are the issues in this, and of course degradation is issue with the majority of the things. So pinhole means, suppose you have a actually you don't deposit layer very uniformly, and there are holes where this material and this material get connected to each other, and so it will provide a easy path for electrons and hole pairs to recombine rather than going to the external circuit. So if we just see like earlier, so if sunlight falls in a solar cell, it can get reflected away also, because same rules apply here also. If it doesn't get reflected, it get couples. This is a positive. Then if photon will be absorbed only when the band gap is suitable. This also you always remember. This is applicable to this is applicable everywhere. So if photon is not absorbed, it transmits, it is a loss. So the positive is, suppose it gets absorbed. So these are loss mechanism. So if it get absorbed, then not necessarily that all the photons which are absorbed will create excitons, but majority will. So suppose it has created exciton, then this exciton can recombine. There is a high probability. Let us assume it doesn't recombine, then it will create free charges. So when it will create free charges, when there is an sufficient energy is activation energy is there, which is usually at the boundaries. So suppose a free electron free charges or electron hole pair is created, then it is still possible that it can back recombine. So if it recombines, that is again lost. But if it doesn't recombine, we are even more optimistic, then these charges will be separated by the built-in electric field, which has been provided now by what? The work function difference of both the electrodes. Now, if still they can recombine at the boundaries, because boundaries are always providing dangling bonds, which is actually extra energy states. So if they do not recombine, then these are collected at the electrodes. So when these are collected at the electrodes, then only these will flow through the external circuits. And so all these loss mechanisms has to be, ideally they should be zero. You cannot make it zero for sure. So we have to minimize this. So if we see the efficiency, total efficiency, we can, all these processes which we see, which we just saw, can be combined together. One is, what is light absorption efficiency? How much light has been absorbed? First is optical efficiency. How much light has been we can say entered in this material. It gives you an optical efficiency. Then how much portion of that you can say entered light has been absorbed, that will give the light absorption efficiency. Then out of them, how much of those photons, absorbed photons, has produced excitons, that will, and then then the exciton should diffuse also, that is the exciton diffusion efficiency. Then there is a charge transfer efficiency, how much charge which is generated actually has moved and moved to the electrodes. Then now last is this charge collection efficiency. So all these are less than 1, actually very less than 1 in these kind of solar cells. So the efficiency, you keep on multiply all those things, and then you get the efficiency. This is an example of typical organic polymers or molecules. See, this is our solar spectrum, which we saw, part of solar spectrum between 300 to 1200 range. And you have the typical molecules which are using, like P3HT is one molecule, one polymer, PCBM is one molecule. This is another polymer. So if we see P3HT, the absorption is this much only. So this entire portion is not at all absorbed. So if something is not absorbed, it is obviously a loss. So light is falling. Suppose light of this wavelength is falling on your organic solar cell. It is of no use because it will not be absorbed at all. It will be transmitted. So you need to find out material which is having a broad, very broad, you can say, kind of absorption. So this gives how much light is absorbed. It depends on your band gap. So if it depends on band gap, then if we select a material which is having very low band gap, so first thing is that if we choose a material which is having a zero band gap, obviously they are metals, then can they work as a solar cell? No. Though entire light will be absorbed, but it cannot be used as a solar cell. So let us try to see here what is the difference if we try to use low band gap or higher band gap materials. So the answer is no. How? So this is the energy levels of donor, and these are the energy levels of acceptor. Typically, the voltage which is generated in a solar cell is the difference of this level to this level. So it is the LUMO of acceptor to the HOMO of the donor. This is also an estimated value. So if you, as I like in just a few moments ago, I said if you use a metal or a material which is very close to metal, what will happen? This will become zero. So that your voltage will be zero. If your voltage is zero, then there will not be any power, because any current multiplied by zero, first thing there will not be any current. But if at all there is a current, then it will be multiplied by zero, so power will be zero. So now if you try to have these two very close to each other, now the voltage will be reduced. If the voltage is reduced, though current will be increased. So voltage will be lost, but even if current is improved, overall you will not be benefited. In the ideal case, when both the you can say levels are matching, then the electron transfer can take place, but still the voltage is reduced. So if you can bring it down here, in that case, suppose this electron, because these are matching, there will be resonant tunneling transfer of this electron from this level to this level. So current will be very high, but voltage is still less. So it is not that you can always use low band gap material and or selecting a material in which HOMO of one and LUMO of one are very close to each other. So you can have an efficient electron transfer or better excitant dissociation efficiency. But still, because of less voltage, it will not be very useful to you. Now, there is another point. What are the time scales? So suppose a photon is absorbed and an excitant is produced. This is excitant. So, and they are at the boundary only. So the time scale of this excitant dissociation is very small. It is at the level of femtosecond. However, the then it can actually dissociate if it moves here. Now, if you see if it is not moving to this place, then there is a recombination. And because of that recombination, what is we are getting? We are getting if it is a radiative recombination, we are getting photon out of that approximately of the same value which was absorbed. So this is called as a photoluminescence also. So this time scale is of nanosecond order. And as I said, even if you have actually separated this electron and hole exciton into electron and hole pairs, but still this electron and this hole can still combine by back transfer, but the time scale is even low. So this probability, though it exists, but it is very low as compared to this and as compared to this. So if it reaches somehow at the boundary, in that case, it's a very highly probable that the electron exciton will get dissociated. Still, it can recombine, but you can say the time scale is very high. So it favors in this. So this ratio of number of excitons reaching interface to total number of excitons created defines exciton dissociation efficiency. This is just to explain. Charge transfer efficiency is electron and holes drifted towards electrodes. On the way, they may get trapped, recombined. The ratio of total charge reaching electrodes to total conducting charge created at the interface defines charge transfer efficiency. These I have already explained you earlier. Now, let us try to see some of the materials which are used in these kind of solar cells. First thing is the transparent conducting electrodes. So these are ITO and FTO are two materials which are most commonly used. For the active layer in this kind of solar cells, these are typical donor type of materials, MD, MO, PPV, P3ST, which is most widely studied material, and these PCDTBT, PTB7. These are donor polymers are mostly, and then acceptor for parylene, fullerene, PCBM 60, 70, 71, and other fullerene derivatives. These are typical acceptor molecules which we use in the bulk heterojunction solar cells. Then for electron transport or hole blocking layers, lithium fluoride, that is zinc doped tin oxide, titanium oxide, and these materials are for hole blocking layer or electron transport layer. So electron transport layer you can call as hole blocking layer also. And similarly, hole transport layer is also called as electron blocking layer. So P dot PSS, most commonly used material, MoAO3, V2O3, NiO, WO3 are some of the materials which are used as hole transport layer very commonly. For the back contact, obviously you will need some metals and aluminum, gold, calcium, silver. These are some of the common materials used for the back contacts. However, when you want to select such materials, you need to take care of the work function of this material and then the HOMO-LUMO levels of the your donor and acceptors. On the basis of that only, you will be able to decide a correct back contact material. Then how to fabricate using physical vapor deposition, chemical vapor deposition, that we will these deposition techniques we will see in maybe day after tomorrow's means the last lecture. And then for like solution techniques, spin casting, Doppler blading, self-assembly spray also, these are used for deposition. The problems with bulk heterojunction solar cells are these are having small absorption width. It must be very clear to you by now, and therefore you can use multi layers also, but that is also not of very help. efficiency are very low, and the life is also small. So these are the current problem with bulk heterojunction solar cells. So this is it just a structure. You have the typical structure of the solar cell. So you have bulk heterojunction solar cell. You have ITO, that is transparent conducting oxide. You have aluminum, another electrode. And then there's an active layer. What is this active layer? This active layer is this blend of your donor and acceptor, as we explained in earlier. And then you have an electron transport layer or hole blocking layer, which is of very small thickness deposited over here and very close to the this contact. And similarly, you have a hole transporting layer of P dot PSS you deposit over the transparent conducting oxide, and it extracts hole out of this active layer. So I have a small animation which will clear everything. So how the device is fabricated, this is I will just explain in next slide, because one animation I have made, it will clear actually all these things. These are the typical you can say parameters or values which we use in our fabrication in our laboratories. So first thing is it is patterned by chemical etching. Then P dot PSS is deposited by spin casting, and then some heat treatment is given. Then active layer is deposited by blending this first thing. These two. This is your donor. This is your acceptor. You mix them, both of them together, and blend it for several days. After that, you will have a very good blended material, and that material is then spin casted over P dot PSS. So you have ITO over that you deposited hole transport layer, spin casting, then you deposited this blend. Then after that you have deposited a thin lithium fluoride layer, very thin lithium fluoride layer, that is electron transporting layer, and then aluminum electrodes over that by thermal evaporation. Just the same thing I will try to explain through a animation also. So this is glass, and so typically this kind of thing you get from the market when you have an ITO coated glass. So over this glass, the entire portion has been covered by ITO. So what you have to do, first you have to pattern. So this patterning is done by chemical etching. So with the chemical etching, you get this kind of structures, and then over this you deposit a hole transport layer by spin casting, as I explained earlier class in earlier slide. Then you deposit an active layer by again spin casting. See, you will not get exactly this kind of cubical or you can say beautiful shapes, but you will get just this is to explain you. Then you deposit a small, very thin lithium fluoride layer by thermal evaporation, and then over that by shadow masking you deposit the aluminum electrode. So now you have this and this in. So basically now you will have actually 9 devices, 3 devices this way, where there will be this will be overlapping with this. Then you can imagine you will have the structure where you will have ITO, then P dot PSS, then your active layer, then lithium fluoride, and the electrode. Now this portion, this one is connected. Uh, this is connected to this. This is connected to this one. So suppose now this has become your solar cell, working solar cell. Now suppose light fall and it falls on the active layer. So an exciton is generated. Suppose it reaches at the boundary before it recombines. Obviously, electron hole pair will be generated separated, and then these will be collected at respective electrodes, and after they will flow through this external circuit through this load, and current will flow, and you will get a copper devices. Then all, because these materials are you can say they degrade in atmosphere, so therefore sealing is also important. So this device has to be sealed. These are you can say actual photographs of typical like patterning, then spin coating, then deposition of active layer using spin coating only. Then this is for aluminum deposition. You have a mask here. Over this, you have placed the devices here. Then you will get a final PSC device like this. Small devices, these are experimental devices. And then for IV characterization, what you have to do, see, you have to make one contact at the top, one contact at the bottom. So this is one, you can say, strip. This is another strip you connected here. So actually, this time you will be measuring this device. These are some of the photographs. These are from our lab only. So this is a flexible solar cell, polymer solar cell. This is also a flexible polymer solar cells, which gives about 15 volt and 0.3 milliampere currents, and it was stable for about 8 months. And this is the you can say typical. Now this was the regarding the polymer solar cells. Next class of devices comes as a dye sensitized solar cells. So dye sensitized solar cells are differs from conventional organic solar cells in a way that dye is used for absorption. Dye is basically a colored you can say compound which absorb certain radiation. So a dye differs from semiconductor absorber bulk heterojunction, and it only performs as the absorption function and generally has no role in the transport. So the role of dye is only to absorb. But like in bulk heterojunction, it was the same material was playing a role of transport also. But here it is not a very good conducting material. So what it does, it absorbs, and immediately the electron hole pairs are generated. You collect the electron through some other assembly, and then you collect the hole through the other assembly. That also we will see those suitable assembly. You have to devise those suitable assembly. So here there are a lot more problems as compared to bulk heterojunction, because first thing is that you have to find a suitable material which actually collect that electron very fast before it recombines. Similarly, the hole which has been created in the dye, it should also be immediately replenished with some electron, so that there is no probability or less probability of the back recombination. So in conventional DSSCs, electrolyte with ion conduction instead of electron is used for regeneration of the dye. We'll see this later. So this is a typical DSSC device, you can say sketch. So in which you have a glass over this, like there was ITO, here people are using FTO, similar transparent conducting oxide, but its energy level is matching with TiO2. So then you have a TiO2, and then over TiO2 you deposit the dye, a very thin layer of the dye. So what dye does? Dye actually absorb the radiation, and electron hole pair are generated. Now this electron is immediately, see, this is the you can say level of dye. So if a photon falls, electron and hole pairs are generated. So there you have electron. Here you have you can say absence of electron. Then immediately before it recombines, it is collected by this TiO2. That is the reason. So this the probability of this transfer is much more higher than this transport. So there is sorry, this recombination. So then now you have separated, electron has come here. This electron from TiO2, it will be transported to this FTO, and then from this FTO it will move through this way. Now electron will come here. So now what will happen? You have a electrolyte. That electrolyte is, so this electrolyte is lithium iodide. So you have this you are chemist, so you know very well this I3 minus and 3I minus pair. So this electron is collected by this, and then it get converted into 3I. Now what happens? See, this hole which was left, now it needs an electron. So this electron will be taken from this 3I, it goes here, and it gets converted back into I3. So effectively what has happened? This electron which we has moved, suppose there was one electron here. So this electron has first thing excited to this level by absorption of photon. That electron moves here, it goes to TiO2. From TiO2 it goes to FTO. From FTO it comes this way, this way, this way. Here there is a platinum counter electrode. From this platinum it goes here. What it does, it reduces this to 3i minus, and then after this 3i, then this electron so is actually taken by this level. So electron has reached at its original place. However, in this process there are three you can say it has changed you can say state at three different locations. First here, then here, then here. So the probability of transport from this electron from this to this electrolyte is has to be reduced. It should be very less. Otherwise, this electron which is reached here can directly come here and convert this I3 into 3I. That is also possibility, but it is less probable. So dye-sensitized electrolyte solar cells show high efficiency, relatively more as compared to the polymer solar cells. However, they have been saturated because you can see there are so many things which has to be working in tandem. This level, this dye, you should have, first thing you should find a suitable dye. Next thing is there should be a material which is having close to very close energy level, and this probability of this electron transfer transport should be also very high, so that it doesn't recombine. And then it should be matching with the level of your transmitting conducting oxide also, so that it moves from this way. Then you should have a suitable appropriately you can say this redox couple also, which is having means energy levels matching with these two. So you will actually there are only few you can say combinations, ideal combinations possible, and because of them the research is not actually has taken up much on DSSCs, and it is quite saturated for so many years. So this is just I have written once again what I have explained you verbally. So this is this 3i plus, it takes electron, and no, so this 3i plus it actually release electron and get converted into I3 minus, and then again by taking electron, this takes electron and get converted. So all of the processes in DSS are kinetic. Their efficiency is determined by how fast they occur relative to competing reverse process. So you see, you saw there are three different processes. I have made one animation also. In next slide I will show. So that will give you a very good feeling of how these processes are relative to each other, and how actually this will be giving you better efficiency. So let us see how a typical DSSC is made, and then how it works. As I shown in polymer solar cells, once again I will show you. This will give you a very good picture or very clear idea. So how a device is made. So anybody can make it very easily, of course with little bit efforts and seeing somewhere. So this is a FTO coated glass which is available in the market. So over this glass, what you need, if someone can tell, so you need TiO2. So first thing is a very small TiO2 compact layer is deposited, very small. Then over this TiO2 nanoparticles, spherical size nanoparticles are deposited. Why do we deposit this in the nanoparticles? Because this way you can increase the surface area. Now over this, at this entire assembly, this is called as the photoanode, and then this entire assembly is dipped inside a die. So this was the situation. Now you dip inside a die, you keep there for some optimized times. Then what you will get over the entire you can say TiO2 in ideal case, let us imagine in ideal case, so your entire TiO2, all these fair surfaces have been, you can say, deposited with dye. So all the surfaces are now covered with the dye. So TiO2 is not now exposed to this area, but actually it is having, it has covered entire thing. So if now light will fall on, if I allow light to fall here, it will not be absorbed here because it's a glass. It will not be absorbed here because it is transparent conducting oxide, transparent conducting oxide. So it is transparent to glass, but it is conducting at the same time. So the now electron will then this TiO2 layer also, because it's a very thin layer, and it is transparent also to that. So it will move here, and where it will reach, it will not reach to these TiO2s, but it will actually, this entire TiO2 spheres are covered with the dye. So this will be absorbed by this dye. So now this is photoanode we have made. Now on the other side, we will have a small another glass, you can say, or whatever thing you want, just to cover, and then a small, you can say, very thin layer of the platinum. So it is used as a counter electrode. Then this entire assembly is sealed. Entire assembly is sealed because you have to fill this electrolyte. Then you fill it with the electrolyte, and then you seal it perfectly, and then one connection is made between this point and the PCO. Now this, the dye, the energy level of dye I have just drawn like this. So there are some three different levels. So this will be your LUMO, this will be your LUMO, this will be your HOMO. So suppose light falls, that what light falls, what will happen? Electron will be excited from this level to this level. Let us see what happens. So light falls, then this electron, it leaves a hole, electron moves here, and then it immediately collected by this TiO2, and then through this, it is again here, it's a TiO2, it goes from this to this, and then it is collected from this. So let us see once again. So just see all the three processes. One is slow, one is fast. This is very fast. This is moving here. From here, this electron is coming. It is actually combining with this, and it is converting here. At the same time, this electron, this hole which was generated here, this has been, you can say, accomplished by the electron which has been collected from here. However, at the same time, one electron comes from here and it makes again to I3. This you know. So these are these processes, these which I have explained. I think just I will once again display this, so it will give you a clear picture how a DSSC works. Okay, done. So now let us see what are different characteristics required for the materials which are actually we are using. Can we replace it? Of course, we can replace if we can find an alternative which is having the same properties or better properties. So TiO2 is preferred. Why it is preferred? Because it is relatively inert, cheap, and has low recombination of charge carriers. TiO2 has this is also commercially available 20 to 30 nanometer particles, and the band gap is also about 3.2 electron volt. So it is a good. Then TiO2 can be sintered to provide good contact between particles. And then transport of carriers in TiO2 occurs by diffusion. Diffusion length of carrier should be larger than thickness of the oxide. Carriers in conduction band of TiO2 may be lost by reducing to I3 by back reaction. This is also possible. The electron which we saw, actually it was moving to TiO2. In place of moving to TiO2, it can go back to I3 also. So this, but this, it's less probable. So now what are the properties for a good dye? So you can find out another material. See, you can think you can devise your own DSSC with different kind of materials, but you need to, you can say, see all those materials should be following certain relation to each other. What are the properties for a good dye? They should be having good absorption, and it should be the level should be close to the metal oxide surface. Then significant overlap with the solar spectrum. Why it should be significant overlap? Because if there is no overlap, it will not be actually absorbed at all. So for the good absorption, yeah, you can, if you can find a dye which is very good, if it is absorbing entire spectrum, suppose of this slightly black color, then it will be very good. Fast kinetic of electron injector, this also important characteristic. And then it should be stable for many million cycles, because it should not happen that you have designed everything, you have made a solar cell, and then you have commercialized it, and within 1 month the person who have purchased comes and say our system has stopped working. So this is again the same thing. I'll very quickly explain that to prepare the photoanode. So a thin layer of TiO2. These things I have already actually explained. So these are the values of typical few micron. It is deposited. Then over that TiO2 nanoparticles are deposited, and then it is treated by this TiCl4 for half hour at 80 degree centigrade. So these things you can do at your lab also if you want to make such kind of solar cells. It's very easy. Now, as I said, the counter electrode is also required. What is counter electrode? Is any material, preferably whatever material you want. Over that you need a very thin layer of platinum. So for making a thin layer of platinum, what we do, this is a chloroplatinic acid, and then what is that? So then this is make so you can deposit over FTO substrate itself. So you have FTO substrate, so that is also conducting. Over that you deposit this, and then heat it. So then this decomposes into platinum. So what you will get effectively glass. Over that glass you have FTO, or over FTO you will have a very thin layer of the platinum. These are some of the photographs. This is like film deposition of TiO2. Then after that, once you have deposited TiO2 film, then you dip it inside a dye. This is dye. You keep it here. So as you see, it was white. Now the dye has deposited over the TiO2, so the color will become of the color of dye. Then this is the counter electrode. This is FTO coated glass. Over that, this chloroplatinic acid is, you can say, by brush we have just spread and heated it. Then you okay, bring them both together, seal it perfectly, and fill inside the electrolyte. So this was DSSC. Now, what was the problem with the DSC? First problem is this liquid. Whatever way you prepare it, there's a probability this liquid is going to seep out. So once your liquid goes out, your DSSC stopped working. So this is a bigger problem, a very big problem. So first thing is that leakage and evaporation of liquid. Then it degrades also, and then some components are hazardous. At the cost of platinum is also one issue, because platinum is expensive. Even if layer is very thin, still it is expensive, and the stabilities are poor. So what we should do? Can we replace it with something solid? This liquid, of course, we can do. We can find out some. We have found out some solids, and if we can replace these solids in place of this liquid, then the DSSC should be, at least these problems should be removed. But of course these problems are removed, but then you had many other problems. Those were added. So what was that material? This material is full transporter Spiro and OMETAD, and this is very expensive. Only it can be imported. So you can use this, and all other things are same, like it was in the DSSC. So this way we can make a solid state dye sensitized solar cell where liquid is not there. So this problem of liquid is removed, but that is also, this is also very unstable material. So if we see in a solid state dye sensitized solar cell, liquid electrolyte is replaced with inorganic p-type semiconductor or organic hole conductor. So whole conductor, it should be, why it should be whole conductor? Because the job of this electrolyte was actually to compensate that hole which was created when light was absorbed by dye and electron has gone top and then it was collected by TiO2. So this hole which was left, it has to be you can say compensated. So you have, if you have a good hole transporting material, now on the level of that should be matching with the level of the dye. The level of the energy level of that HTL material should be matching with the level of dye. So if you change the dye, your material will be, obviously it has to be changed. So in few other cases, polymer electrolyte by conduction is by ions is used in place of the liquid electrolyte. These consist of mesoporous TiO2. People use mesoporous TiO2 with monolayer of dye and hole conducting material penetrating into pores of TiO2. So problem with solid hole transport materials, of course there are many problems. So these are, because these are solids, first problem is that since it's a solid, filling of pore inside TiO2 matrix is difficult. And why it is important? See, you must have seen we have many spheres of TiO2 over one another. We have just added to increase the surface area, because liquid electrolyte is a liquid, so it can go inside, but solid cannot go so easily inside those. So then the contact with the dye to the electrolyte will be very less. So it is very difficult. One is this difficulty. So though we have solved one problem, but we have added many more problems. And then Hall mobility in inorganic semiconductor is lower than that of electrolyte. That is another problem. If you are having a solid organic semiconductor also. So we have seen in the first few slides that organic semiconductors are having very low mobility as compared to inorganic. So the conductivity is going to be low. Mobility and conductivity are obviously related. Then the combination of conduction band electron of TiO2 is higher compared to electrolyte, compared to liquid electrolyte. Actually this so ideal hole transport material should have valence band slightly above energy of oxidized dye. This I already explained, because it should be matching. So electron, if their levels are, the energy levels are matching, then only this electron transport can take place. You just cannot put any arbitrary material and start imagining that, okay, my electron will move. Electron or holes can only move from one place to another place, one material to another material, if their levels are exactly matching. If it is exactly matching, then there will be a resonant transport. If they are slightly, it should be lower, at least slightly lower. Even if it's slightly higher, then also there is a probability they can move. But if it is, they are very much having, they have a very big offset, in that case, it is not possible to transport. So you just cannot put any material anywhere, not in DSSC or in any other device. You need material in case if you want to have transport of carriers. In that case, your levels, energy levels should be matching very precisely. In ideal case, slightly offset is okay. They can have less transport efficiency, but still they can work. So some of the hole conducting materials that have commonly used are CuBr, CuSCN, and Spiro. This is imported. This is actually most commonly, but it is also not very stable and very expensive also. Now next comes the, so this now we have seen polymer solar cells, we have seen bulk heterojunction polymer solar cells, we have seen dye sensitized solar cells, we have seen the dye-sensitized solar cells, we have seen the solid-state dye-sensitized solar cells. So in all the solar cells, they like first thing is that the radiation which is being falling on these solar cells, it has to be first absorbed. Then once it is absorbed, then electron hole pair has to be generated, separated electron hole pair. Then those electron hole pair should be you can say extracted from that, and it should be these should be brought out to the external circuit so that the current can flow there. So these dye-sensitized solar cells, solid-state dye-sensitized solar cells, and perovskite solar cells are quite similar. So first thing is that in this you not exactly similar, but consider principle wise they are same. So suppose in place of dye, let us I'll explain in a very simple way. In place of dye, suppose I use an perovskite material, and perovskite material which are not all perovskite material, but certain perovskite materials. Uh, Actually, it is by chance that this is a perovskite material which suits all these things. So it is not that any perovskite materials, because we are using that perovskite material, that's why we call these solar cells as the perovskite solar cell. So suppose now you have a dye sensitized solar cell. Now we change it to, now you have a solid state dye sensitized solar cell of any other configuration rather than we saw in last one. And then in place of dye, you use as an absorber some material which is actually having a perovskite structure. You can use any material, you can have some other structure also, but what the property should be having, or what property this perovskite material has, why it is so successful, it is having a very high absorption coefficient. How it helps? Then it actually helps in absorbing the radiation. Then it is a very high carrier mobility. So carrier moves inside this very fast as compared to the dyes. Then you have a long carrier diffusion length. So diffusion length is approximately in the range of microns. So mobility is also very high, say, as compared to organics. And so 1 micron is very reasonable thickness. Then direct and tunable band gap of this perovskite material. And so this perovskite material is actually C3NH3 PbI3. Why we call it perovskite? Because it crystallizes in a perovskite structure. What is perovskite structure is? This is the perovskite structure. This you must have studied earlier in inorganic can say crystal structures also. Then it has a high radiative efficiency, and then room temperature solution based fabrication is also possible. So this is a typical structure of perovskite. So because we are running out of the time, so now I will go quickly. So just you can say slightly different than DSSC, but for understanding, imagine that in place of DSSC, in place of dye in solid state DSSC, we have placed it. So this will other things will remain not exactly same, but you can correlate. So now your dye in place of dye, your perovskite will absorb, and then from that perovskite, the electron will transport. So there are three different PSC structures. You can have you have glass, then you have FTO, any transparent conducting oxide, then you have a hole transport layer over no, this is actually TiO2 layer, a compact TiO2 layer. Then you have a hole transporting material, which we saw in like DSSC, solid state DSSC, something solid. So you have that material, you have filled that material, and before that, what you do, you actually now in place of TiO2, because the levels of TiO2 doesn't match with this perovskite. So though principle wise same, but as I said earlier also that if you need to change anything, you have to find a matching, find matching everything. So for that, it's aluminum oxide is the matching one. So you have, so now over the first you deposit this, then you deposit compact TiO2 layer, then this TiO2 layer, over this you have Al2 oxide, over this you deposit the perovskite. People use TiO2 also in place of aluminum oxide. That also work, but this is better. So here, like here, they have used TiO2 only. It is TiO2, and over that TiO2, but this time this is perovskite, anti-perovskite. So these are you can just see one by one all these things. These are different type of structures where the perovskite solar cells are made. So then work on perovskite solar cell. I will just quickly go through this. Started in 2009 with the use as a sensitizer in DSSC. This dye is called as a sensitizer. Why it's called sensitizer? Because actually it doesn't do anything other than absorption. So material, this is the material, methyl ammonium lead iodide. Why we call it peroxide? Because it's crystallized in the perovskite structure, AbO3. Semiconductor having band gap. These things low exciton binding energy of 0.03 electron volt. It ensures dissociation into electron hole pairs. Then a small effective mass of electrons and holes with mobility of more than 7 and 15 centimeters square per volt second, and carrier lifetime as 100 of nanoseconds. Diffusion length is more than 100 nanometer. Very good. Theoretical study shows that defects created only shallow traps that do not cause carriers to recombine. If traps are very, you can say very close, it's the probability is very high that the electron will get trapped there. But if this in this material only shallow traps are generated, which do not cause these carriers to recombine or to get trapped also in some cases. So current best efficiency of perovskite solar cells are 25.5%, slightly more to that. Recent developments include PSC made by dipping and spraying techniques and without hole transporting layers that simplifies process. Most materials are inorganic and less likely to degrade, though some component, actually it is called as, it is not purely inorganic, organic solar cell, it is also called as hybrid solar cell. Like in the polymer solar cells or bulk heterojunctions, both the components were purely organic. So in that sense, if you try to call perovskite solar cells, these are called as the hybrid solar cells in case of organic solar cells. So typical operation of 1,000 towers has been carried out without noticeable degradation. So there are some issues which are very open in these perovskites. First thing is stresses. So because if you draw IV curve, you will see both doesn't match. Then stability of devices in the field need. It is also not very stable. Then there is a component which is lead in this. So that lead is toxic. So people are trying to replace this lead for so many years. Many attempts has been done. Tin is tried many times, but it is not completely successful. It is giving some good results. Then extensive degradation in presence of moisture, air, and temperature. Doping with chlorine, bromine ions, and studies using other inorganic perovskites. These are the perovskite solar cells, which is fabricated in our lab. So this is and this is the, you can say, the efficiency means JV curve. So you have voltage here and you have current density here, and you can see how the current is moving. Now next comes the quantum dot solar cell. First thing, the same here, we are using quantum dots as absorbers. Now, what are quantum dots? Quantum dots are some material. When we have a 3D crystalline structure of infinite length, then things are different. You must have studied the you can say the quantum well problem, where an electron the energy levels are found out inside a very thin quantum well. So if you try to reduce the size of the atom, which was size of the crystal, which was ideally infinite, to only one or two atoms or three atoms level, in that case, what will happen? It will not be now an infinite crystal lattice. So the potential will not be periodic potential will not be infinite. So if you try to solve this problem using Schrodinger equation, you will find some different energy levels. So by changing the size, cluster size, and let it remain in a periodic way, you can actually change the energy levels. You can alter the energy levels, and then absorption of or absorption or emission, because the energy levels now you have changed. So absorption or emission will now take place as per these new levels. So why we call quantum? Because the size is very low. Dot means because we have now very few atoms, and the energy levels will be corresponding to those levels. Though material, in ideal case, even if you have silicon, then it will not have the band gap of 1.1 electron volt or valence band and conduction band, because now it is only 4-5 atoms. If you have 4-5 atoms, maximum you will get four closely spaced levels top and four closely spaced at the bottom. So and then if you try to solve the energy level for Schrodinger equation, try to find out the allowed energy levels or possible energy levels, you will find that with changing this size, with changing the clusters, with changing the numbers, with changing the distance, you can actually tune the property. So you have dots, you have very small dots, because they are very small. So it is not a 3D entire, you can say, infinite long 3D phenomena which was we were studying earlier. So here the quantum effects are more predominant. That's why we call these as quantum dots, because size is such a low size where quantum mechanics is only the solution. So quantum dots. So these are quantum dots. You understood what is quantum dots? Quantum dots are the materials with the you can say only few the thickness or the diameter or the size of these are very small, but all are same, all are identical. So quantum dots provide possibility of multi-exciton generation as well as up and down conversion of photons. So again, you remember, it is not like valence band and conduction band. It is not like HOMO and LUMO also, because in HOMO LUMO you can HOMO and LUMO you have the cluster size is very large. However, in case of quantum dots, this is also the size is also very small. So you can make semiconductor quantum dot materials of some materials. There are plenty of materials, thousands of materials which you can make, but these are the common materials people are doing research, because these give good results. Lead sulfide, CDC, and indium phosphide also, and some ternary compound. So synthesis of quantum dots, the synthesis of colloidal quantum dots of diameter typically 2 to 50 nanometer is carried out by using precursor compounds dissolved in the solution and organic surfactants. This is how we make. Then temperature of the process is very critical. There should not be any agglomeration. See, now earlier what we were trying to do, we were trying to make a structure which is infinitely long. Now we are trying to reduce the structure, and size should not increase. Size should remain within that you can say range only. So, but there is a means they tend to increase. The atoms try to come and attached to either and increase the size. So agglomeration is also a big issue that has to be stopped, and there are many methods to stop agglomeration, and having the size of quantum dots to a desired level, keeping the size of quantum dots to a desired level. Temperature of process is very critical, and some surfactant also plays a very role. So now it's otherwise the similar structure. You have FTO, you have TiO2 barrier, then you have TiO2, and over that you have actually deposit now in place of earlier we deposited dyes. Now then we deposited perovskite materials. Now we are depositing quantum dots. So these materials will also change depending upon the level. So it will not be necessarily same. But generally now, because we have done these things, we have already optimized TiO2 this process. So the quantum dot also we select which are having the energy levels very close to the our assembly. So you have a grave. Now we try to find out some dead body of the same size. So the same quantum dots we try to find and then try to study. For best quantum D solids available, the thickness is about 1 micron is needed for absorption, while diffusion length is about 100. This I think similar. Therefore, bulk heterojunctions type of structure is needed. Important materials are TiO2, zinc oxide, lead sulfide, Di2O3, and these are MO3 and other hole extracting materials, anti-reflection coatings, etc. They are similar. Once you have understood one type of solar cells and entire assembly, entire fabrication process, then you have understood almost each things. They are more or less same with slightly with small changes here and there. So this is like a quantum junction solar cells with PNN type layers from these quantum dots. And this is also like you have a glass substrate, and then you have ITO, which is the transparent conducting oxide. I will again say transparent conducting oxide. So indium tin oxide is transparent but conducting. Usually the conductors are not transparent, or I would say metals are never transparent because there is no band gap. So whatever photon falls, they will immediately absorb. They will not allow it to pass through. Then you deposit P dot PSS, which is a whole transporting layer, and then quantum dot in P3ST, you can say in the P3ST and quantum dots, and then you have a metal cathode here, and then you can connect this through external circuit. Sorry, yeah, and then the current will flow as the light falls. So with this, if we summarize, the best efficiency, I'll just say the best efficiency of for single crystalline silicon is 27.6%. For gallium arsenide, it is 32.9%. Polycrystalline silicon, it gives 23.3%. This is for the best and not commercial, but in laboratory scale. CIS 23.4, CDT 22.1, amorphous stabilized 14%. But if you go to the market and if you have the silicon stabilized amorphous silicon solar cell, like in your home calculator, and you try to measure the efficiency, you will hardly find efficiency above than 8-9%. But still, 9% is also reasonable efficiency, and it gives sufficient power which can run your calculator for years together. And the life of these solar cells are very high. I have shown you yesterday in our own, we have the solar cells which are about 40 years old, and they have not degraded. They are same as it is. Only thing is the deposition, like silver or some electrode are faded, but otherwise they are perfectly working. Then presently some recent research has shown that bulk heterogeneous solar cells can give you up to 18.2% DSSC. This is 13, nearly 13 for about 6-7 years. Then perovskite is 25.5, and quantum dot solar cells is 18.1%. This the recent, very recent, you can find the recent efficiency at this site. So this is typical. If you have solar cell, then this I have summarized everything here. Silicon semiconductor solar cell, there are two type. So solar cell, if we say silicon solar cell, there crystalline, non-crystalline. Then you have amorphous. In crystalline, you have single crystals and polycrystalline. The efficiency. These are of the commercial. I'm talking about. Commercial means on the large scale. Then polycrystalline 10 to 13%. Non-crystalline amorphous, as I said, 7 to 10%. And for compound semiconductor, gallium arsenide, it gives 18 to 30%, mainly used in the space applications. Because why? Because first thing is gallium arsenide is a direct band gap semiconductor, so it has a definitely the absorption is better. The optoelectronic properties are also better, and there is no issue. We don't use gallium arsenide in our domestic purpose. First thing is it's expensive. Next thing is that arsenic is toxic, and we will see maybe day after tomorrow in the class that making crystal of gallium arsenide is also very, very difficult. Then organic semiconductors, DSSC and organic type of layer, these are only some for which some devices are available in the market, and these are typically 7 to 8% and 2 to 3%. If you, why I once again say, if the efficiency of these devices are how it is calculated, what is your electrical energy output, that is the maximum in ideal case. But when you have a panel, you don't know what is the maximum ideal VP or IP. In that case, whatever maximum electrical energy output you are getting, and whatever light is incident on solar cell, and you multiply it by 100, then you get the percentage. Now, if you put at maybe when sun is at 45 degree and it is there is no dust, there is no cloud, and everything is perfect, then you get about 100 milliwatt per centimeter square incident energy on the solar cell. So this is a car slightly maybe 2 years old for the efficiencies. I think we have already crossed the time, so I should close it here. And if you have any question, I am ready to answer. No, Discord. So if there is any question, you can ask. I'm ready to answer here. Otherwise, you can send it to me via email also. My email address is on the front of every lecture on the first slide. No questions? So if there are no questions, then thank you. See you in the next class. Then we will see some thermoelectric materials and the remaining portion we'll try to cover in 2 lectures. Thank you.